Hello and welcome to the lecture on curves, which is given within the series of computer graphics lectures at KAUST. Let's start with some clarification. What is the meaning of the word curve, or what could be the possible meanings? One way to interpret the term curve is an actual image of a curve, which is then residing in an two-dimensional, three-dimensional, or generally an n-dimensional space. The second definition of a curve is the actual continuous map between some one-dimensional space and some n-dimensional space within which this curve from the first definition would exist. And the curve can be seen as either an finally rendered curve, or it can be also understood as something which is being drawn. So, for example, for parametric curves, we will have a parameter t, which will be varying from, let's say, 0 to 1. And depend on this increasing of the parameter, we will be increasingly drawing the curve. So our curves, which we have represented digitally on computers, although they would be optimally fully continuous, they are represented by large sets of points. And generally speaking, each point has two neighbors, the previous point and the next point. However, this doesn't hold for the endpoints, of course. Sometimes the curves do not have endpoints because either they are infinitely long, like for example a line, or they are closed, like for example a circle. We have several curves which have distinct names, and we have a specific visual representation already developed for these type of curves. For example, lines, ellipses, circles, and arcs. But then we have a large group of curves which are none of these and are somehow more complex. And this we simply put into under the definition of the free-form curves. We can define curves in various ways. One way to define a curve, and you already know this representation quite well, is an implicit representation of a curve. This means that for two-dimensional space, function which curve which lies in two-dimensional space, we will have this implicit function where the points on the curve will be those who satisfy this following equation. With this, we will have an advantage that even for points which are lying outside the curve, we will be able to quickly compute how distant they are from the curve. However, we will not be really able to tell what is or give an order to the points on an implicit curve. This is in contrast to the parametric curve representation, where the parameter gives us this notion of the order. So parametric representation has one free parameter for a curve, and that varies over a defined interval. Typically, we would have an interval between 0 and 1, or other larger intervals, maybe always between two integers. There will be some segment of the curve defined. And this parameter serves as an index to the points on the curve. So, and keep in mind that these points can be of multiple dimensions. It could be points in 2 dimensions, it could be points in 3 dimensions, it could be points in more dimensions. We can also see the parameter as a time that defines the progression of the curve drawing. And please keep in mind that the function of parametric representation is a vector valued function. So we have a mapping from R to Rn. For R, we have our parameter t, and in Rn, we will have our coordinates of those points, x, y, maybe z, etc. And then there is another type of curves which are also popular in computer graphics, but they do not fit into any of these two categories, such as, for example, some subdivision schemes or the fractal curves, like, for example, the Koch curve. Let me explain you what I mean. What is a Koch curve? Have you heard about Koch curve before? Well, Koch curve is a fractal where we have first its initial state, so to say, and then we have, for each iteration, we have defined a shape which replaces the original segment of this curve. So this is our initial state, and this is our iterator, if you like, and this iterator will always replace the straight segments. So this is the situation in the set of zeroth initial state, and in the first state we will have, in the first iteration, we will replace this line by these 4 line segments. And in the second step, we will be replacing these 4 line segments by each segment by other 4 line segments. Oops. So, and then it will look approximately like this. And let's draw the final, for me, the final third iteration, where we will have the first segment, the second segment, the third segment, the fourth segment, and I have just drawn this part so far, and you can imagine how this continues for the rest of the third iteration, and you can also imagine how it goes for further iterations. This type of generation of fractals is called the iterative function system, IFS. If you are interested to learn more about fractals or IFS, you can check it out. Also, the famous L system generation of trees and natural objects falls into the same category. So this is a procedural generation of a curve, the Koch curve, and if we would have the initial state given as a triangle, we will actually create the so-called Koch flake, snowflake, through this fractal generation, is another class of curves which are often used in computer graphics. However, we will not be dealing with those too much on this lecture. We will give clearly the most focus to the parametric representation of the curves because they are mostly used. So, as you already know, the parametric curve is defined through an parameter t, which is defined on an interval, and by the function which maps this parameter t onto the coordinates of points of our curve. This is a vector valued function. And we can have various parametrizations. So, for example, our t is varying between a and b, which might be some values, let's say -100 and 100, and we can have the same curve represented by a different parametrization. For example, by reparametrizing it into the range 0 and 1. So what can we do about it? How can we reparameterize it? Well, we will introduce a reparameterization function, GU, which takes the values of the original parameter intervals and maps it to 0 and 1, as you can see here. Now, if we put this parameterization, this U is then varying between 0 and 1, and you can see that it will generate us the actual t value, which will then be used for the function evaluation of the function f. But as we are dealing with the u, which is u belongs to 0 and 1, we have another function, f2, which simply is remapping the u onto the parameter t, and then the parameter t is used for evaluating the function f. So this is a reparameterization function, and by this we can change the parameterization to an arbitrary one. And there is infinite number of parameterizations, and they will all lead to the same curve once they are finally drawn. However, there might be a difference on how they are drawn. Let's have a look at this. For example, imagine that we have a parameterization between 0 and 1 and of u, and this u is now drawing us this following line. For x and y, we have the following value. So if we draw it, we have for u equals 0, we will have 0.00, and for u1, we will have the 0.11, and for example, for the point u equals 0.5, we will have the functional value 0.5, 0.5. So this is 0.5, this is 1, 0.5, 1. And basically our line looks like this, which is the function f. Let's call it f1. Then we have another function, let's say f2, then we have another function, f3. And they actually, if you look at them, they also have the parameter u going between 0 and 1, but they are always squaring this parameter. So for example, for 0 and 1, they would both have the result of 0 and 0, 0 and or 1, 1 points. But for the point or u equals 0.5, this function f2, so f2 for 0.5 will have which coordinates will it map to? Will equal to 0.25, 0.25, which is different from the previous function f1. So if we finally draw this function f2, it will look exactly the same. I will just draw it with an orange color. It will also look like this. However, for u equals 0.5, the value will be here, while for the other function f1, the value is located here. So, and then if we look at the function f3, the same will happen. The value u will vary between 0 and 1, and then finally a drawn curve will be varying between this 0 and 1 interval. So it will map to points 0, 0, 1, 1, and all the others where the x and y coordinates are identical. However, for example, fu equals f3u equals 0.5, the u power 0.5 powered by 5 will be something very small, so it will be something 0, 0, and the same will hold for the y parameter. So you can see that we will be for the u equals 0.5, we will be here in the very beginning of, and then at the end, we will be quickly drawing the rest of the curve. So while I will just draw it here, while the first F1 parameterization will draw the curve in a constant speed, the second will draw it in such a speed profile, and the third one will be a long time nothing is happening, and then suddenly the curve will be drawn. So this is the difference between the curve once it's drawn. There is, as we can call it, and the parameter is somewhat invisible element and is defining how fast the curve is being drawn. And with this parameterization, we would often, for example, like to have that the curve is drawn by a constant speed. And for that to happen, we will need to perform the so-called arc length parameterization, unless the curve is already arc length parameterized. So arc length parameterization means that we will create a mapping of the parameter such that an equal distance of steps in the parameter will result in equal distances on our curve. So let's imagine that these are the equal distances, and we can see that, for example, here, this is an equal distance between the first and, let's say, the second, but the distance on the curve here is definitely not equal. These two segments, the second segment is shorter than the first segment, and the third segment is even shorter, fourth segment is even shorter. So this curve is definitely not arc length parameterized. The distance between the samples within the sampling of the uniform sampling of the parameter interval doesn't lead to equal distances on the curve. Once the curve is drawn, it doesn't really matter, but imagine that we will be using this curve as a guide for a camera. So we are animating the camera positions in computer animation, and the camera should follow this curve, and we will here have somehow a feeling on this representation of the curve as being on a roller coaster, because here we are going very fast, and here we are very slow, then again here very fast, traversing the curve. So this might be desired if we want to make a camera on a roller coaster, but it is not desired in general. So in general, we have to have the parameterization under control, and it is often the case that we need to reparameterize the curve. For the parameterization, it means that there are equal steps between the individual uniformly distant parameter values are equal distances on the curve. And this can be analytically described as that the small functional segments and the segments of our parameter space are forming a constant value. This is not changing. And we can express it in a way that we are computing our arc length first, and then based on the computing the arc length at a particular position, we can perform a reparameterization. So we will have another parameter, no longer maybe the parameter t, but another parameter, which will be then changing such that the arc length increments will be constant, with the new parameter will be then sampled uniformly. And so how do we compute this arc length parametrization? We can see it on the expressed here analytically as an integral of small, infinitely small line segments on the function. So, and it is this arc length parametrization is then defined on a certain interval of the parameter t between the points ta and tb. So if we will be evaluating this curve on an interval where this is a and this is b, with this formula, we will be basically defining how long is this segment. Exactly. But we cannot express this arc length always in an exact way, and often we need to resort to numerical computations. So the simple numerical computation here would be that we will be simply summing up linear segments between our functional samples or points on our curve. And that will approximate us the arc length. So this is essentially the length of this infinitesimal segment of our curve. And how can it be computed? Well, we can see that there are derivatives of our function with respect to different coordinates x, y, and z um, by our parameter u. And so we basically derive a function for each of the coordinates, and then we simply square them and sum them up. And finally, in order to find out the length, we perform the square root operation, as we are used to from all other calculations of an Euclidean distance. So let's have a look at one example here, how this can be achieved. We have an cubic curve representation, which is a parametric curve. You see that this is a vector valued function, and in each vector component, we have a cubic curve parameterized by the same parameter u. So we have here x is one coefficient, bx another coefficient, cx another coefficient, always associated with a different degree of the polynomial. And we can simply perform an derivation operation on each of these coordinates with respect to u. So we know how to do it, and we can see that if we derive the first component, x coordinate, we have this formula, the same formula with different coefficient y, ay, by, cy is for the y coordinate, and analogously for the z coordinate. So we have this, we have actually performed this derivation, and now we can square all these, as we said, and sum them up. And finally, we perform the square root. Oops. And we are done with our computation of the um, arc length for a very small area. So these values will be basically coming into this integral. We will then perform the integration on a specific interval and between TA and TB, and then we will compute the arc length for that segment defined by the interval within the parameter. So this is the arc length parametrization, and this can, once we know the arc length, then we can reparameterize our function or our parametric representation of the curve, so that with constantly increasing the parameter, we will be stepping in a constant distances on our curve. Often, we are simplifying our representation of the curve by not being one single continuous curve, but being several segments, piecewise parametric representation of a more complex curve can be achieved this way. So you can see that here the function f parameterized by the parameter u will be then parameterized so that half of this parameter interval will be applied for function f1 and half of this parameter interval it will be applied for the function f2. So here, if our parameter u is smaller than 0.5, the u will start, or this parametric value will start between 0, and as it is twice 0.5, it will go between 0 and 1. And here, in the second case, we see 2u, so if the parameter is 0.5 and higher, it will start with 2u, 2 times 0.5 is 1, minus 1 is 0. So this will be starting from 0, and once the u is 1, this will be 2 minus 1 is 1. So it will be also varying between 0 and 1 for the function f1 and f2. So we are here also reparametrizing our small function segments so that we can define on our interval for u between 0 and 1 actually two functions. And it is important that these two functions somehow meet, because there where one function ends, so let's say this is f1, and we are now drawing the function f1, and here this is the point u equals 0. Here we have the value u equals 0.5. This is f1. And the f2, it will be important that this function starts, so f2 0.0 is equal to f1 for 1. Then we will have, so this is written here, then we will be saying that our piecewise parametric curve is continuous curve. But otherwise, if this will not be, this condition is not fulfilled, it will be discontinuous. And then it will be probably pointless to talk about it as being one curve. Here we had just two linear segments, which are sort of concatenated into one piecewise parametric representation. That doesn't need to be the case always. The functions can be arbitrary. So here we can see a concatenation of a linear segment and of a circular segment. But often we are having the functions of the same degree in case we are dealing with polynomials. The simplest polynomial representation will be concatenation of linear segments. So how complex this piecewise representation should be? Well, it should be as simple to compute as possible, but at the same time, it should result into visually pleasing representation. So in case we want to simulate a smooth curve, these linear segments here will be probably resulting in an undesired representation, while having a more complex curve can be more desired. However, we can simply use more linear segments here, and by that achieve a more better approximation of the curve by this set of linear segments. Let's talk about smooth representation for curve, which is called splines. The term spline is coming from crafts where it was essentially a metallic piece which is reasonably stiff and which has been placed and constrained between uh, some elements like these nails here, and the endpoints were fixated, and this created a smooth piece of metal which was then possible to trace in order to create a curve. And this has been used in manufacturing in the past. We are using this metaphor of a spline in computer graphics, and we can use for spline a piecewise polynomial function, which means that each spline will be defined by a set of polynomial functions. It could be linear functions, quadratic functions, cubic functions, or even higher order functions. And with these polynomial functions, we can describe their properties uh, in, in various ways. So there will be some global properties related to these functions and also some local properties. Keep in mind that these are often content of a differential geometry course, and we have such one at KAUST as well, which you might be interested to check out. The local properties define you per point continuity, whether the function is continuous at a particular position. It defines you the position or the derived attributes such as the direction or the tangent or the curvature, etc. So for a piecewise polynomial representation, we need to secure the continuity across the connection point. So where the parameter is changing from one functional description to another one. If it is continuous within the segment but not continuous across this connection point, then we will say that the curve is discontinuous. However, we have several levels of continuity. So, for example, if we have a curve which will look approximately like this, let's say, and then at this position here, we will have a continuity. However, the first order derivative there will not be continuous because it will be different value for one segment of the curve than for another segment of the curve. So in such a case, we will be talking about C0 continuity because it is continuous only in the function, but not in its first order derivative. If we, however, have the continuity across the functional values at this point and at the same time the first order derivatives, so these two values are also equal, then we are talking about the C1 continuity, meaning that the continuity is also in the first order derivative. And if that holds, and in addition, we have the continuity in the second order derivative, then we will be talking about C2 continuity. So it is continuous also for the second order derivative. And we can go further and further, and the more continuity this curve has across this connection point, the smoother the curve will be. We can observe several examples of continuity in this image. So this will be a C0 continuity because there is a discontinuity, obviously, in the first order derivative in these two linear segments. One has the value minus 1, while the other value will be likely 1 as a derivative for this line segment. So this is C0 continuity. This will be C1 continuity. So we can see that the derivative here is the same. However, if we look at the curvature closer, in this case, they will not be the same. So it will be only C1 continuous, which is already a great continuity, and that we will perceive these curves as smooth. C2 continuity has the same curvature value at this point. So we can see that there is a clear smoothness, and this will be, for example, advantageous if we want to perform a camera path also across such a point. Then we will make sure that if C2 is continuous, then the uh, the camera motion will be smooth as well. And then we have something which is termed as a geometric continuity. So it is rather related to a finally rendered curve, whether it is smooth or not. And we are talking about the G1 continuity or G2 continuity. And here the result basically is that we will have the same tangent at this connectivity at this point, which will be, let's say, like this tangent, and in another tangent from this line will be the same. I mean, of course, they will be the same, but it will be in the same direction, but it will be differently scaled. So we have some kind of scaling in the differences of our nth order derivative, but in principle, with this scaling, this there is the continuity. The same would hold for the G2 continuity. So the curvature on one side of the segment is a multiplication of the curvature on the other side of the segment. So it is only that the derivatives match in the G geometric continuity, but the magnitude differs, and it is less restrictive. However, in the following parts of our lecture, we will be mostly focusing on the C type of continuity. So as I mentioned, the C2 continuity would be great for example, camera motion, because the discontinuity in the second order derivative would be more noticeable in motion. However, we not only use computer graphics for depiction of lines or for using these lines or curves as for animating cameras, lights, or objects. We are also using it for manufacturing. So therefore, if we are manufacturing objects which should, for example, be exposed to certain flow, then discontinuity even in the fifth order derivative might cause a turbulence in aerodynamic manufacturing. So the continuity requirements are varying from application to application. And if we are only interested in finally rendered lines without any animation of cameras or so, then certainly our continuity can be less restrictive than in case of manufacturing applications. In the following, we will be discussing piecewise polynomial curve representation, and the general description or the general formula for polynomial function is the following formula here, where the highest exponent value will define the degree of the polynomial function. So this can be also rewritten. As we can see, it is a sum of the polynomial terms into a more compact representation, the so-called canonical form of a polynomial, where we see the sum over various coefficients associated with an polynomial variable, and these are then iterated with the iterator from 0 to n. So t powered by 0 will be, of course, 1, and it will be corresponding to the a0 coefficient. So this could be also reformulated in a slightly different sum, where we have somehow not such a simple polynomial function, but we have a more complex function, which is itself somehow a polynomial function containing several polynomial terms and not just only one. And then we will have a certain coefficients associated with this each polynomial function, and their sum will be forming us the piecewise polynomial curve. So often we will be dealing with more, so if it's not a linear segments, but the polynomials will be, for example, cubics, then we will have overlapping functions, so to say, which are contributing to the position of along the curve, and these are more complex polynomials than just a single term polynomial. Let's now develop an interesting and valuable framework how we can define our curves. And we will be discussing it on a simple, almost trivial example of line segments. So the line segment function can be defined in a very simple way, and that is a parametric representation can look, for example, like this. We will be familiar with that and can immediately interpret that there is one point P0 from which we start, and then is the point P1, which is the end of our linear segment, and between those two we are smoothly interpolating. So at the beginning, when the u is 0, then 1 times 1 minus 0 is 1 p0 plus 0 times p1. So it will be, for the f0, it will be p0, and for the f1, what will happen? This term will be cancelled for u equals 1, and 1 times p1 will be p1. This is clear. And please keep in mind that this is a vector valued function, which we are now, as are the points here, these are having several components. For example, in 2 dimensions, they will have 2 components. So while we will be not talking about that explicitly, keep in mind that it is we are dealing with several components independently. The u is sort of connecting these two components. So for one value of u, you will have a pair or a triple or more, for more dimensional spaces in which the curve exists, representations or coordinates of the points along the curve. So these points, which we have the P0 and P1, will be the control points, are the control points of our curve. So often we would like to define our curve by some control points. So I have now defined my linear segment between the point as the points P0 and P1, and this will define me this linear segment. It is intuitive to define the curves through such control points. For the lines, this is trivial. For more complex polynomials, higher degree polynomials, this will be somehow points which should which the function should go across, or at least should be attracting our curve towards these points. However, this is not the only way how we are defining the curves. For example, for the line segment, we can define it as through a position in the center, and then orientation and length. So we will have just one point, and then we will have maybe an orientation and the length of that entire line segment. Or we have one endpoint, and then we have the second endpoint defined by the relative to the first. So basically, we have a vector to the second endpoint. Or we have a midpoint and one endpoint. So we have one endpoint and one midpoint, and the second midpoint will be then defined by doubling this vector between the midpoint and the first endpoint. So there are several definitions how we can define a line segment, and all these definitions, as we will see, are possible to use within a generic framework on how to define our lines or how to define our curves, because the lines are simply just first-degree polynomials. So back to our description, which is a parametric description of a curve, where we have the two known points, which are our inputs, and then we have our parameter u, which is then defining us how the line segment is being formed. This is trivial for a linear case, but it will be not so trivial for the higher degree polynomials. And remember, we were describing that our canonical description of a curve or polynomial will be as the sequence of a coefficients and then the sequence of the variables or the parameter u. And that means for a linear function, the form looks like this. We have one a0 coefficient and then one coefficient which is associated with our parameter u. But this is different than the previous parametric definition of a curve, and we do not know really these parameters a0 and a1. So, but what we know is that our function fu can be expressed this way, as we see, where we have the u is a vector of the various polynomial degrees of u, and the coefficients a, which is again a vector valued coefficient, because for each coordinate it has a different value, or it has a separate value. Now, what we know, however, that for our f0 parameter, it should be equal, this function should be giving us the p0 point. And in this description of the a0 coefficients, this leads to that if we put in this description, let me remove some of these into this description, we have the a0 and a1. So here we have somehow an invisible 1 value, and here we have a value which is coming from the u, which is the multiplier of this coefficient. So for the f0, we have here 1, because there is no u which could change that. And for the second position, for the a1, we have 0, because u is equal to 0. And that gives us, multiplying with the coefficients a0 and a1, equals that a0 is equal to p0. And then for the f1, we will have this row vector, will have 1 here again, but here for u equals 1, there will be 1, so we have 1 here, and therefore we will come to the conclusion that the a1 is actually equal to P1 minus P0, which is the vector between the uh, between the first point and the second point. So this sort of reformulates our definition of the curve from two endpoints into one endpoint and the vector to the other endpoint. So what is this good for? We can now formulate our representation of our curve, and this holds for the line segment, but also for higher degree polynomials, through known input points, which are here, the control points, as we said, and then based on their known points, the corresponding coefficients which are associated with our A vector. So A0 will always have 1 here in this case because it is not having a U. But for the P0 case, the U is 0, and therefore the 0 is here in this matrix. For the P1, the U is 1, and therefore this multiplier with A1 will be 1. So once again, we have this A0 plus A1 or UA1, and I will write it 1 times A0 plus UA1, and that leads to this, to writing these values into the corresponding rows of this matrix. So it holds that once we multiply these coefficients with the matrix, we will get to our points. This matrix C we call a constraint matrix, and it defines the constraints of our parameter U. So, but we typically these are typically the unknowns, and these are the points are typically the knowns. So we do not need to calculate the piece based on the matrix and the polynomial multipliers. Opposite of that, we need to calculate the A so that we know the canonical form of our polynomials given certain points. How can we do that? Well, we know it from linear algebra that the vector A we can calculate by putting the C matrix onto the other side of the equation. So as and that is described here on the bottom, where the A is equal to inverse matrix of the constraint matrix, which is then multiplied by our input points P. And the nice thing is that this constraint matrix is now defined as the basis matrix, and can be associated with our points P, but also can be to find out the A, but can be also associated with the parameter U, and through that we will find out what is the what are the values not only at these points P, but once we know the A, we can find out what are the values between the known points. So the unknown points can be calculated from this formulation. As we have defined the line segment based on the first endpoint and the second endpoint in the previous slide or the previous example, here we have a case where we are having a midpoint defined, P0. P0 is the midpoint, and P1 will be one of the endpoints when the U equals 1. So, and here we can see the universality of this approach, because the constraint matrix can be equally generated from such a case. Here we will have, therefore, the coefficients 1, here 0.5, not 0 anymore, and the second row will be the same. If we invert this constraint matrix, we get the basis matrix, which will look like this. And from that matrix, we can then directly compute what will be our values for A0 and A1. As, of course, vectors, meaning that for each coordinate we will have a separate value. And as we see, this doesn't only apply to two endpoints, but to various definitions of a linear segment, and it also applies to various definitions of higher degree polynomials. So for example, we have here a description of a quadratic polynomial, which quadratic polynomial could form as something like a parabola or other quadratic structures. So we can see here that the description for quadratic formula is shown here, which will mean that we have three elements which we will put into the matrix for each of our points which are defining the constraints. So we will have one point P0, which will be at the start of our quadratic polynomial curve. This will form the F0. And then we will have the second point, P1, which will be in the middle of the parameter range. And then we will have P2, which will be at the end of parameter range between 0 and 1. And we can see that this parameter is now put into the formula where we have at the beginning we have this u powered by 0, so this all will be ones, and the rest will be 0, 0.5, 1, 0, 0.51, and then for the quadratic term we will have 0 powered by 2, 0.5 powered by 2, and 1 powered by 2. So we put all these coefficients now nicely into our constraint matrix as we have done previously, only that it is now a 3 by 3 matrix. We invert it again, get the constraint matrix inverted into the basis matrix, and this basis matrix we can then use for calculating our coefficients. And by that, we will obtain our formula Fu, where we will have the coefficient A0 plus U times A1 plus U squared A2. And that will be then our desired formula, which will then pass through our points P0, P1, and P2 exactly as we have defined it, with the constraints that the P0 will be at the beginning, P1 will be in the middle of the parameter range, and P2 will be at the end. Now, this matrix form can also accept not only the constraints of the function, but also of the derivatives of the function. So not only the points, but also a vectors at the particular value corresponding to the u, or even curvature value. So what do we need to do in such a case? Well, we will simply derive our formula for the quadratic polynomial, and we will obtain a linear polynomial where we will have the term a1 and the term a2 will be remaining, the a0 will be out, and then we will have a different coefficient here because of the principles of the derivation. This is a general formula not only for the quadratic polynomial, but for any higher degree polynomial, actually of an nth degree. And this is the first order derivative formula. Here we have the second order derivative formula. So let's have a look if we have again a quadratic polynomial which we are searching for with the following constraints. We have only one point defined, and that is in the middle. Then we have another we call it a control point, but it's not really a point, it's a constraint. And the constraint is that the first order derivative at this position 0.5 will have the following coefficients associated with A1 and A2. And then we have even one more control constraint where that the second order derivative is having the value 2 as the coefficient next to A2, and the rest of the coefficients will be 0. So as we have it, we can put this into our constraint matrix, and this constraint matrix will then give us through the inversion, we will obtain the basis matrix. And from this basis matrix, again, through a system of linear equations, we can obtain the values for the A0 and Y1 and A2, which satisfy those constraints which we have specified. We have previously defined the A coefficients as being obtained from the basis matrix and the input constraints defined by the points or the derivatives of the derivative constraints. Now, and while here we have our vector of various degrees of the u parameter. So u powered by 0, u powered by 1, u powered by 2, and etc. We can now replace the description of this canonical form of our polynomial. Instead of a, we can put the information, the original information, basis times the points. And now we can, through the associativity, now put these u and b together and then have the points defined separately. And this will form us as the u and b will form us an polynomials, which will be those polynomials which we will be multiplying with the point p. And maybe you remember where we have defined that the canonical form can have a form of more complex polynomials, and those are exactly these polynomials. These polynomials will be typically not have only one term, but will consist of several terms. And these polynomials will be then multiplied with our point or control point and summed up together and blended together with this blending function. And the result will be the position of our on our curve for the specific value of the parameter u. So this means that we can have the basis functions defined independently from the points, and the points can be, or the control points can be then put in separately, and we will through that define always a slightly different curve. So these basis functions, which we will generate, this bi with our parameter u, we can formulate them through different procedures. And one such a procedure is called Lagrange polynomials, where we are defining the basis functions through product of based on the values of u, which are our knots within the parameter range. So if our parameter range goes from 0 to 1, let's say, we can have our u values where we have our points defined or control points defined are separating this interval by several points. Let's say here we have 0.25 and here we have 0.75, and then we have, let's say, also at value 1. So this will be our UI values. So these are then U1 will be 0.25, U2 will be 0.75, and U3 will be 1. Also, we are not limited to the range 0, 1. We can have also our U defined as 0, 1, 2, 3, 4. So our points are are associated with different parameter values, and the curve is simply by filling the space between these points. In some sense, it is similar to resampling, and here we are using a specific resampling function which we are defining through our basis functions. So let's have a look what this is about, these Lagrange polynomials. For example, a 3 points 0, 1, 2, we will then have our values for u1 will be 0, u2 will be 1, and u3 will be 2. So let's find out how do we calculate such basis functions. Here we have the definition of it. So it will be a multiplication between these rational terms. So we will start as u minus, and now u minus uj, which j goes from j equals 0 to n, but the j is not equal to I, and our I is currently 1. So that term we skip and we go to the next one. So u minus u2 divided by 1 minus, so we can actually, instead of u2, we can directly give there the value 1, u minus 1, and here we will have the value from the denominator, which will be 1 minus 2, 0 minus 1 times, and the other term will be u minus 1 minus 2, and again it will be 0 minus 2. So this will be the first term of our Lagrange polynomial. We will have 2 more of such ones, and always multiplied by the corresponding point. So let's have a look at this and then on the next slide. So again, we have said that we have 0, 1, 2 for our u values, and we already know the first term, which is u minus 1, and here we have 0 minus 1, which is minus 1, and here we have times u minus 2 divided by minus 2. This is our first B1 u blending function. The B2 blending function will be equal to u minus 0 and 1 minus 0 times u minus 2, 1 minus 2, which is equal to u, let's put it under 1 times u minus 2, and this will be minus 1. And the third polynomial will be b3u is equal to, and now we have u minus 0, 2 minus 0 times u minus 1 divided by 2 minus 1 equals 2. and this is u half times u minus 1 divided by 1. So these are our three polynomials, and our final function fu will be equal to p1 u times p1 plus b2 u times p2 plus b3 u times p3. So this is an interpolating function, which will be now a quadratic function. As we can see, these terms will be of a quadratic degree. And these basis functions, which we have here, will be each multiplied with the corresponding point which they are supposed to be interpolating through. And we can, however, change the u, and the u will now go between 0 and 2 to fully draw our interpolating polynomial. While such polynomial will be interpolating, these Lagrange polynomials have the following disadvantage. They will be defined as global. So if we are adding one more point here, then we completely need to recalculate our basis functions, and our curve will globally change. So just adding one more point will change how this function looks like. Also, such a Lagrange polynomial will result into heavy overshooting, because in order to interpolate through certain points, there will be an undesired artifacts of overshooting. Therefore, such curves will often be undesired for practical applications. But the Lagrange polynomial, on the other hand, are the most simple ones to explain and to understand that our parametric representation of a degree 2 can be defined by 3 points, and these points can be arbitrarily placed onto the parameter range, and they can be actually put in after we define our basis functions. So we can have always different input points. The basis functions will stay the same. Always for a quadratic polynomial, we will have the same basis functions. For cubic polynomial, we will have always the same basis functions. Just the points will be differing, which will be always defining as a different curve. Let's look at how the basis functions will look like for piecewise parametric functions. We can see here that our parameter range is between 0 and 1, and our u is split into two halves of subintervals, one defined for one function and one defined for another function. And we can see if we want to create a piecewise linear segments between 3 points, we will be using basis functions which we already are familiar with. You remember previously we have defined our definition of our linear interpolation in this way, where we have 1 minus u multiplication with one point, with the starting point, plus u multiplied with the end point. And similar description will hold also for the f2u. We will just have here the p2, and here we will have the p3. Otherwise, the same formulation will remain. And we can see here that the 1 minus u is one basis function and u is another basis function. We can see it perhaps a little bit better on this plot here. We see that the basis function 1 minus u is actually this one. This is the first basis function, which is then 0 afterwards, after 0.5. And the second basis function is the function u. Oops. And then after 0.5, we have again two basis functions. Again, the b2u, which is then 1 minus 1 minus u, and then again a function u. So, and we see that these basis functions are actually the same ones as we started off with when we wanted to calculate our coefficients a0 to an for an n polynomial function. So if we somehow came back to the basis functions and realized that we had them available at the first place for the linear interpolation, at least. For higher degree polynomials, we didn't have them because they are not that straightforward to derive, but for the linear interpolation, they are somehow obvious. We can see here one more precise definition of our basis function v1u, and for our linear interpolation or piecewise linear degree polynomial, so a straight lines concatenated into a polyline of two segments, we will have here the following description. We have here three terms, you see, because there are three basis functions, although the first basis function is only defined on the range from 0 to 0.5, and the third basis function is only defined from the range 0.5 to 1. The B2 basis function is defined over the entire range, and therefore we will have here all the three terms and all the 3 points which are given at input. But for example, for the first segment, this third term will be always 0. Similarly, for the second segment, this first term will be always 0. When we are having several segments, then we need to ensure, in order to create one continuous curve, that these segments are connected together and form continuity. And this can be formed by having a so-called shared point scheme. So our points are defining the curve on segments, but the shared points will be always where these two curves will be meeting at a certain point. So that is one approach how we can form a continuous segments representation. And the other one will be a dependency scheme. So we will not have defined the endpoint explicitly, but this endpoint will be computed from the previous segment. And from that segment, we will be starting the curve will be continuing for the second part of its parameter interval. So we can understand it as in the first case, we are having explicit definition of points, while in the second case, we will have maybe a point and a vector. So we do not have the point available at the very beginning. We must first compute it. And once we compute it, then we have another vector from which will be defining our segment, how it continues further after the second point. For both schemes where we are putting the segments of the curve together, share point or dependency, it holds that the total number of points must be less than n times m, where n is the number of segments and m is the number of control points per segment. For linear segments, we will have, for example, n plus 1 control points. And let's have a look whether this is true. So we will have now 5 points, and we will have 1, 2, 3, 4 linear segments. So this holds. For the dependency scheme, we need to understand that it lacks locality. So whatever we will change on the curve, it will propagate throughout the curve to the rest of it, because we are defining the positions of points or curvatures or derivatives based on the previous segments. And once we change something in those previous segments, this information will be propagated to the further segments of our curve. Therefore, the dependency scheme is then not local in general, and will propagate the changes throughout the curve. We can see that on the following examples. While for the shared point scheme, we see here that there is a locality in change. We are having here a polyline, a curve, piecewise linear curve, and these piecewise segments are sharing the endpoints, as we can see here. And if we change one of these endpoints, the other endpoints are staying as they were defined. They are not changing. So the change of one endpoint doesn't really affect the other endpoints and doesn't really affect many curves, a few curves which are in the neighborhood of the affected or edited point. This is not the case for the dependency scheme, as we said, because we can see here an example where our curve is essentially defined by an endpoint or start point and a center point. And if we are changing the center point at some point, at some position, then we will be changing also the second endpoint position. And as the slope of the relation between the center point and endpoint is sort of copied from the previous segment, then we can see that our zigzag structure is becoming much more shallower after our change. So we can see while that the first segment was not affected, but all the other segments have been affected until the end of the curve through this dependency scheme. The most popular polynomial function for representing curves in graphics and graphics applications are cubics. So this means a third order degree polynomial. They represent a reasonable trade-off between a speed of computation and the flexibility of application, because they can form various shapes already, but at the same time, they are reasonably simple. They offer the C2 continuity, which means that they are already applicable for applications which involve time. And they also still provide minimum curvature interpolants. So they are not overshooting and creating too complex curves, so to say. The description, the formula for cubics is described here, where we have 4 A coefficients, and then our highest degree term is the U powered by 3. We can have as control points positions or derivatives, first order derivatives, or second order derivatives. There are various cubics which we can use, and they often have various properties. There are four interesting properties which the cubic can satisfy. First, that each piece of the curve is a cubic. Then that it interpolates the control points, that it has a local control, which means that a small change will be only changing the curve locally, and other segments will be, which are more far away, will be unaffected, and that it has a C2 continuity. And we know only cubics which can satisfy simultaneously three out of these four properties. So sometime we need to have a trade-off and decide which properties are for us the most relevant. The continuity of such a piecewise cubic curve is measured at knots. So the continuity itself is these curves in the middle of their definition. They are, of course, continuous as cubics are. However, whether the continuity is C0, C1, or C2 is defined at the knots. So there where the control points are associated with a certain value of the u, of the parameter u. Let's have a look at one example of cubics, the natural cubics spline, which is defined through position of endpoints and the first and second order derivatives at the start point. So here we will imagine we have just at the first point, we are defining for f equals 0, we are defining its position, its first order derivative, and the second order derivative. We know how to calculate this already, so this is not in the same way as we did it for the quadratic functions or for the linear functions. And the last constraint is the P3, which is the position of the first endpoint of the first segment of these natural cubics. Of course, for piecewise cubics, we will have then P4 will be then defined at F2, and P5 will be defined at F3, etc., which will be the positions of our points, and the corresponding derivatives will be computed later on. So this curve, natural cubic, will come somehow to this F1 position, and we don't know how at the beginning of our curve construction. It will have some derivative value, first order derivative value, and it will have some curvature, which will depend on how this curve will be defined through its A0, A1, A2, and A3 coordinates. Now, for the second segment, once we are reaching the parameter value F1, we will have its derivative values available, and those will be used to create the second segment. And this second segment will then, therefore, have at the end of drawing this second segment, at the P4, we will know what are the derivative values and can start to draw the third segment between P4 and P5, and etc. And we can see that this natural cubic is satisfying the first property, the second property, and the fourth property. So it is formed by cubic functions, it is interpolative, and it is also of C2 continuity, because the second order derivative, second degree derivative, will be continuous in this case as well. What it will not satisfy is the locality. Natural cubics are not local. So if we change one value, let's say the first order derivative of the first point, this will have affect the rest of the curve. So it is not local, but other properties are satisfied. For the natural cubics, we can generate our constraint matrix exactly in the same way as we have described it before. So from the previous equations, we have for the 0 point and for the first point, we have described our constraint matrix. This will be the row for the first order derivative. This will be the row for the second order derivative. And then after inversion, we obtain our basis matrix for our natural cubics. With this basis matrix, we can then compute our coefficients A0 to A3 so that we can define our cubic this way. Alternatively, we can also create our basis functions, and these basis functions can be then multiplied with the corresponding points, which we will choose at a later point. The second type of cubics are the Hermite cubic functions. These ones are defined slightly differently. They are defined by the first endpoint, second endpoint, and the first order derivative at each endpoint. And this will fully define them through the constraint matrix. So which properties these Hermite cubics satisfy? Well, they will satisfy that all the basis functions are cubics. Also, what will be satisfied is that there is a locality. So if we change one part of our curve, more distant parts of our curve will not be changed. And what also is satisfied is that it is an interpolative curve. What is not satisfied is that it is only C1 continuous. So we do not have a C2 continuity, and therefore Hermite cubics are perhaps not the best choice for making an animated camera path design. How to define this? Well, as simple as we have defined our constraint matrix before. We have 4 control points. At the first endpoint, position and the derivative, second endpoint, the position and derivative. From that, we are calculating, defining our constraint matrix, and where we have the first position, derivative, second position, and the derivative, we invert it and obtain our basis matrix, which can be used for calculating our basis functions. Our basis functions are actually stored in the columns of this basis matrix. I didn't reveal this to you, but if you look at how it is, how these basis functions are calculated, and with which point each basis function is associated, you will see that the column is associated with the, let's say, P0. This column will be associated with the P1. This column will be associated with the P2, and this column will be associated with the P3 point. And each row is associated with a certain degree of u. So the first row will be associated with u powered by 0. The second row will be associated by u powered by 1. The third row will be associated by u powered by 2. And the fourth row will be associated by u powered by 3. So here we have the coefficients which will be always multiplying our u parameter of different degree polynomial. Just to make it even more clearer, if I write now the B0 u polynomial basis function, it will look like this. It will be u powered by 0 times 1 plus u powered by 1 times 0, that's this 0, plus u powered by 2 times minus 3 plus u powered by 3 times 2, which will be then equal to 2u powered by 3 minus 3u powered by 2 plus 1. So this is the first basis function, and we can then, which is associated with the point P0. And so we multiply this term with the point P0. And then we multiply the other terms with the corresponding other points, or better to say control points, because we do not have points only, but also the first order or second order derivatives. And then we have the cardinal cubics. Cardinal cubics are defined through 4 control points, and these 4 control points are also defining us the actual derivatives. So for example, the derivative which is between P2 and so the derivative associated with the point P2 will be calculated as P3 minus P1. So P1, P3 vector will be defining the tangent at the position P2. The same holds for the P3. We will calculate it as P4 minus P2. So P2, P4 vector. So these points are implicitly defining us the derivatives at the points which are in between. So the cardinal cubics will be not using the first and end point for interpolating, only for calculating our derivatives at the other points. So it doesn't go through the first and the last point. And the cardinal cubics are having an additional parameter t. This is not the interpolation parameter, this is a different parameter, which are defining different types of cubics. So this parameter can then be scaling up our how big these vectors should be. And it somehow defines the tangent of the curve. The bigger these vectors are, the stronger the tangent is in that curve. And if we have our t equals 0, so there will be, this term will be equal to 1, then this will be forming the famous Catmull-Rom spline, which is a cardinal cubic, and it has follows the 3 properties that it has the all basis functions are cubics. Then the second is that it has a local property. The third is that it interpolates the control points besides the first and the last one. And the last property is that it is C1 continuous. These cardinal cubics are a little bit more difficult to define the control points. And the reason is that these control points, so for the position, there is no problem. So the P2 is easy to define, and the P3 are just the positions at the endpoints. However, those derivatives, which are calculated from the actual positions, so the derivative for the P2 point is calculated from P3 minus P1, and this leads to the fact that our points are then defined through a certain more complex functions. Nevertheless, this can be, we can establish the relationship between the points and the A coefficients, and from that, eventually, we are able to calculate our constraint matrix. The constraint matrix is then turned into our basis matrix, and then we have our basis functions, which are used for blending the cardinal cubics. We can see in this image how the cardinal cubics look like. We see that they do not interpolate the first and the last endpoint, and the segments in between are defined to be more or less smooth depending on the values of this tangent parameter t, which they have in their definition. We can see that the Catmull-Rom spline, which is this one, is the most least tense one and the most natural one, although it also might in some cases suffer from overshooting artifacts. We can see here a comparison between the Lagrange interpolating polynomial, which is globally defined, and we can see that it has rather high degree of curvature. So this is a high degree polynomial, and it does interpolate, but it is not very natural. We see that if we have this definition of control points, then probably something like this would be a natural connection between the first and the second point. For the cardinal curves, however, we do not have the interpolation between the first and second point, and our interpolation scheme starts from the second point to the one before the last one. But in this area, we can see that the interpolation behaves as we would intuitively expect. The cubic interpolative curves, which we have discussed so far, are one category of curves which could be attractive to use for various tasks associated with computer graphics. The next category would be the approximative curves. This means that the curve is actually not directly going through the control points, like it would be this linear segment, but it is going approximately through these points. Such as, for example, the first example of such an approximative curve will be a Bezier curve. Bezier curve is a curve which is going through the first and the last endpoint, and it is going close enough to the other control points which are defined. Bezier curve could be quadratic, for example, could be cubic, as this one, or it could be of higher degree. And our control polynomial will be always approximated while the points, the endpoints, will be always interpolated. This is the Bezier curve characteristic, and it's one of its characteristics is that it is a non-local approximative curve. So there is slightly a disadvantage. However, we can make it local in such a way that we concatenate various Bezier curves. In particular, what is popular is to concatenate the cubic Bezier curves. So we have one Bezier curve, and we know that it will be going through this point, which is the end point here. And then we can have another Bezier curve. And by sharing the end point, we connect it at that end point. We just need to secure that we have a certain level of continuity. So the fact is that the derivatives for the Bezier curves, so the derivative at the starting position, are defined by the vector between the first, let's say, call it P1 and P2 control points, while the derivative at the endpoint and the second endpoint is defined by the vector between the P3 and P4. So in order to make such a curve C0 continuous, we only need that the two piecewise Bezier curves will be connected through the point P4. If we want to make a C1 continuity, then we will need to secure that the P3, P4 vector is identical with a vector P4, P5. So it has the same orientation and also the same length. Then we will have the C1 continuity. If only the orientation will be secured, but the P5 will be, let's say, a little bit more further away, then we will have the G1 continuity. And we can also, if we place the point P2 and the point P6 in some position, then we can secure the C2 continuity, so that the curvatures at the point P4 will be from both sides the same. More about the Bezier curves on the next slide. So the Bezier curve is defined algebraically as follows. We are having here, and we will be talking about now, about the cubic Bezier curve. Here we have the point P0, so we start the iteration from 0. P0, here we have the point P1, here we have the point P2, and the point P3. As I already told you, the derivative is actually equal to the vector scaled version of the vector P0, P1 or P2, P3. The scaling is by 3. We will soon find out why this is the case. But for now, let's take that as defined, and we will have a look at what is our description of our Bezier curves algebraically. As a cubic, the Fu will be equal to A0 plus A1U plus A2U squared plus A3U cubed. And if we put into the equation 0, what we will end up with? We will end up with the point P0, and at the same time, we will find out that this is equal to A0, because all the other terms in our cubic formula will be 0 due to the U. So we know that P0 is actually A0. For the F1, so the value of this curve will be P3, because that's the end of our parametric curve. And what will that mean? That will mean that all our terms will be associated with 1, because A0 will be there anyways, A1 times 1, A2 times 1 squared, and A3 times 1 cubed will be always there, just multiplied by 1. So we know this, the beginning and the end point. And then we know that our derivative, as we defined it, will be equal to 3 times p1 minus p0, which is the vector p0, p1. And that is equal to, what is that equal to? Let's have a look at what is actually, again, the derivation of the fu. That will be equals to a1 plus 2a2u plus 3 times a3u squared. Now, if we have the starting position, we know that only the first term will be therefore there. So we know that 3 times p1 minus p0 is equal to a1. And what do we know about the derivative at the end position? Well, we know that the u is equal to 1. Therefore, these terms will be as written in the formula for our derivative, always associated with the u equals 1. So here we have the description of what is the correspondence between the points and the coefficient a, and we can actually express what is the relationships, not only if, as we know, for example, p0 here in the first equation, we can enter it into the third equation to find out what is p1. And the same we can do also for the equation 2 and 4, to find out what is the relation between the points P0, P1, P2, and P3 and the A's. Once we know that, we can create our constraint matrix. And once we have our constraint matrix defined, then we can invert it and create our basis matrix. Our basis matrix, I didn't show you here the constraint matrix, you will have to believe me, but the basis matrix looks like this. And we already know that if we take the columns and associate it with the respective points, we will create the formula for our parametric curve. So the formula is here available, and we can see that the point P0 is associated with this polynomial of a degree 3. Here the P1 is associated with another polynomial of a degree 3. The same holds for the P2 and for the P3. So exactly the same as for other cubics, and we can further on describe it, the Bézier curve, through an simplified formulation where we have the sum of the points multiplied by the polynomials, and in this case this will be the basis functions I3, and these basis functions are can be expressed for a cubic in this way. So while these expressions look quite complicated, they can be simplified into a form where it's a multiplication of a u powered by I and 1 minus u powered by 3 minus I, and multiplied by a 3 over I, which you should know what its meaning from combinatorics. Keep in mind that this is not a vector, column vector, but this is actually the 3 over I formulation. All right, let's have a look at it in a more generic. So our basis function, and now this is generic for n control points, or n+1 control points, in fact, of a polynomial of degree n. We need to create this sum, always multiplied with the corresponding point, and we can see here that the basis function is having this formulation, which is actually called the so-called Bernstein polynomials. And from these Bernstein polynomials, we will find out that the formulation actually corresponds to what we described before. So before we described that for a cubic, that the normal at the position of the tangent at the position f0 is 3 times p1 minus p0, and this 3 comes actually for the cubic Bernstein polynomial from this description. So here we are sort of closing the loop. The n over k can be, you should know it, is the n factorial divided by k factorial times n minus k factorial, and it is often for the Bezier curves defined in this way, or termed in this way, C n k, and that's the binomial coefficient which is associated with the product of the polynomials coming from this u k and 1 minus n minus k. So with this formula, this is now a generic formula for the Bezier curves, which can be of arbitrary degree. So, and we can generate one super long Bezier curve, which will be then non-local, and this Bezier curve will then be very smooth. But on the other hand, with any change of a point, the entire curve will change. And if we want to have a locality, we can do it by concatenating lower degree Bezier curves, such as, for example, the cubic Bezier curves. Here you can see it's a sum of the control points, each control point weighted by these Bernstein polynomials, including this binomial coefficient. We can see here that we have a Bezier curve, which is a quadratic Bezier curve. Here we have a cubic Bezier curve. Here we have higher degree, one more higher degree, and one more higher degree. And we can actually see that with a specific placement of our points, we can create a plateau, a straight part on our curve, if we like to. And here we have another example of the Bezier curves of increasingly higher and higher degree. And you can see that while it is an approximative curve, it is very smooth. And that makes its popularity, and therefore it was the curve which has been used, for example, in the automobile industry design, and also Bezier curve was, or maybe still is, the default curve which is used in the Adobe Illustrator. Bezier curves have also the following interesting and useful properties. First property is that they are bounded by the convex hull of the control points. The bounding by a convex hull means, do you know what is a convex hull? Convex hull is if we have some set of points, for example, their convex hull will be a connection of the most outer points so that they form a convex polygon. So this is this will be the convex hull in this case. In the case of our control polygon, the convex hull in this case will be this one here, will be this one here, and will be this one here. So, so it has the convex hull property, which is great, which means that the curve will never go outside the convex hull. Therefore, when we create the control polygon, we might not yet know where the curve exactly will be as an approximative curve, but we will know that it will not leave the convex hull of our control polygon. Very useful property. The second very useful property is the variation diminishing property. Again, it describes us the behavior of the approximative curve with respect to the control polygon. It describes us that if we draw any line in any direction which intersects our control polygon, the curve is intersected no more times than its control polygon, at most the same amount of times as the control polygon, which means that our curve is not having some kind of a weird behavior in between or inside the control polygon. It is smooth and is equally behaving as the control polygon in the sense of its swings or turns. So that's the variation diminishing property, and we can see here that in this first case we are intersecting the control polygon twice and the curve as well twice, and here we are intersecting our control polygon 3 times, and the same amount of 3 times we are intersecting our Bezier curve. And the same holds also in the third case, where we have again 3 intersections, both with the control polygon and the curve as well. Sometimes it might happen that there are less of intersections. Like, for example, if we will be drawing a line like this, we will be still having 3 intersections with our control polygon, but only 1 intersection with our curve. Furthermore, the Bezier curves are symmetric, which means that it doesn't matter what is the first control point and what is the last one. If we have our Bezier curve defined that P0 is here, P1 is here, P2 is here, and P3 is here, it will behave exactly the same. It will look exactly the same as if these points will be ordered in the usual way from left to right. It will be the same polygon. That's why it is symmetric. The curve is also affine invariant, which means that if we now take the control polygon and transform it, scale it, rotate, and skew it, the same operation is performed on the curve itself. So imagine that we take a control polygon, create a Bezier curve out of it, maybe as an approximation of very, very small linear intervals. We will create a very highly approximating piecewise linear curve, which will look exactly as a Bezier curve, and we will perform the same operations on the control points and then of our approximation of our Bezier curve. Then from the control points which are transformed, if we create the Bezier curve again, it will look exactly the same as our approximate representation of the Bezier curve. So this is the affine invariant. And we can have some intuitive geometrically easily explainable algorithms with which we can construct the Bezier curves. So we can construct the Bezier curve algebraically, as we were doing so far with finding out the basis functions and then weighting points with these basis functions, or we can generate these Bezier curves also geometrically. And we will show in the next slides how. But before that, last mentioning, here is a nicer image on the continuity of the Bezier curves. If we have a piecewise concatenated Bezier curves segments into a longer curve, and we want to secure the C1 or G1 continuity, C1 continuity will be secured only if these two segments have the same orientation and length. And if they don't, then, but one is, let's say, a little bit longer, then we have the G1 continuity. As we see here, the position of the previous point or previous points next to the points which are forming as the tangent, their position will be defining as the curvature. And if they are symmetrically placed, then there will be also a continuity in the curvature. So we can actually design or secure the continuity and the concatenated point, but that will restrict us on the placement of the control points. Often in the CAD systems, you will see these points represented. If you want to create a C1 continuity or G1 continuity, then the point, the end point, will be equipped with kind of a double tangent, which will be defining the actual alignment of the curve at this endpoint. So it will force you from the modeling perspective to create a C1 continuous curve, if that is desired. Now let's have a look at the construction of the Bezier curves. Now, one simple example on a quadratic Bezier curve, how can we generate points on this Bezier curve? So for u equals 0.5 or 1/2, here we have the following example. We take our original control polygon and halve its sides. And then we create a third line segment which we connect through these two midpoints. So here we have the expression, the first expression here is 1/2 of P0. So this will be P0, this will be P1, this will be P2. 1/2 of P0 plus 1/2 of Pi1 will be this point. And analogously, 1/2 of P1 and 1/2 of P2 will be this point. And if these points, we take 2/2 of it, we will come up with this point. And now, even if we will be continuing this operation of halving, so we will be now connecting another point here as a half and connecting it here, we will find, and with the half here, we will find out that this point is always staying at its same position. Actually, this point, this orange point, let me clear it up a little bit. This orange point is our, this point is f0.5. So we do 1/2 and, half midpoint and then midpoint of the midpoint. And that is the point through which this Bezier curve is going through. Now, this doesn't only work for the midpoint. This works for arbitrary fraction of our points. So we can have, for example, a point which will be, let's say, 0.25. So this will be this point. And we will connect this point 0.25 with another point 0.25 on our second segment. And then we create again another segment, which will, again, we will find the 0.25 position. And here we will find our point f 0.25. We can see here the description of this geometric meaning. So 1 minus u, well, let's say the u is 75, so that will be 0.25, no, 0. Sorry, the u is 0.25, so 0.75 times p0 plus 0.25 times p1 will end up at this position, and the same holds then for this point here in this in the formula. And furthermore, we are finding the point which is then 0.75 of this point and 0.25 of this point, and then we will find the point at which the Bezier curve will reach the parameter 0.25. And if we now multiply it out, we will find out that we are actually having our Bezier Bernstein polynomials for the quadratic form. So here we can see that we have u and 1 minus u and the 1 minus u squared and so on. So these are all our Bernstein polynomials which can be obtained from this generic formulation which we had on a couple of slides before. So now you understand the geometric meaning of this of the Bezier curve construction. Let's have a look at it once again. We call this construction algorithm the so-called de Castelnau algorithm, and we can see here for a cubic, not quadratic Bezier curve, but cubic Bezier curve, how this is done. Now again, we have a midpoint on each side of the control polygon, then midpoints of these midpoints, and then finally a midpoint. So it's a recursive process, and once we end up just with one segment, this will be our f 0.5. Here we see other examples. For example, when the 0.25 is here, 0.25 is here, this looks like 0.75 is the orange one, which will be then here. So we see that it works somehow reasonably well. Now, sorry, 0.75 is, there is this point here. Let me read it once again properly. Okay, here it is. This is not 0.75, it would be this one. And the same holds here for the 0.25. It's this point and this point. So this will be the f equals 0.25, and this one will be f at the parameter 0.75. So you can now imagine how this will work for even higher degree polynomials of Bezier curves. You have learned how it works for the quadratic, for the cubic, and for a higher degree. It works exactly in the same way. The next category of approximative curves will be the B-splines. B-splines are considered to be generalization of Bezier curves with the following favorable property. They couple the degree of the polynomials which are forming our B-spline and the number of control points. So with Bezier curve, if we will just have one curve, the number of control points will determine us what is the degree of our polynomial which is used for creating the final curve. However, with the B-splines, we can, despite the given number of control points, we can vary what should be the polynomial degree which blends our basis functions. So with the same control points, we can have just a linear concatenation of a polyline or much higher degree polynomials, which will be formed the blending of the functions. And each type of degree will, of course, be affecting smaller or larger neighborhood of parts of the B-spline, meaning when we are moving a point and editing a point position, which is a control point for linear polynomials, then the effect will be rather small, and if it will be for cubic polynomials, the effect of this editing will be visible on a larger part of the curve. Nevertheless, the B-splines as such have a local control, and they do not require to achieve it through such a hack, if you like we have done with the Bezier curves, where we concatenated the Bezier curves into piecewise elements of cubics, for example. So the curve will have, the B-spline curve, final curve will have endpoints, and it is described as a linear combination of the basis functions, as we are used to from the previous cases of our functions. The basis functions are made from k polynomials of degree k minus 1. What is meant by that? That means that, for example, the linear degree, so degree 1, means that this function will be formed by two functions. So it will be a forked function, and there will be two different formulas for various regions defined by our knots within the parameter range. And the continuity is corresponding to it, which will be the continuity k minus 2. So if we have a degree of polynomial degree 1, linear case, then we have k is equal to 2, and 2 minus 2 will be 0. So this, of course, the linear concatenation will result into C0 continuity. We already said that the B-splines have a local control, and it also fulfills the convex hull property similarly to the Bezier curves, and the variation diminishing property is also preserved, as in the case of the Bezier curves. Let's have a look at one example of a linear B-spline. So here the k will be equal to 2, which means that the degree equals k minus 1 is equal to 1. And the continuity is the C0, as we said. Here are the two different functions which I was mentioning, which are defining as our basis functions. So the basis functions, there are two basis functions which are used in this for linear B-splines because there are 2 points and which are contributing to these to these uh, to the values of the linear blend of the linear B-spline. So let's have a look at the formula. What does it say? So the formula says that for I, let's say that I is first one, so this B-spline basis function is u minus 1 if the u is between 1 and 2. So it will be, if u is 1, it will be 0, this value, and it will be then increasing until 2 to the value of 1. So the u, this value will be going from 0 to 1. This is the first part. The second part is the 2 minus u plus I is in this case 1. So we have 2 minus 2 plus I is 3, 3 minus u. 3 minus u is for 2, between 2 and 3. So it will be, if it's 2, then it will be 3 minus 2, it will be 1, and it will go to 3, so it will get to 0. So these are the two parts of our basis function, and one basis function will be used for the one point, the point P1, and the other basis function will be used for the point P2 to form the segment between 2 and 3. So we are starting with the, we are defining our curve only there where the B-spline functions overlap, and in sum, the coefficients are equal to 1. So the area where they do not overlap are automatically equal to 0. So you can also consider this, that the P1 point is weighted with this part of the function, while the P2 is weighted with this part of the function. So this one is with the decreasing one as we are leaving P1, and the increasing one as we are going closer to P2. And why is this the case? You can imagine that the P1 and P2 points are having their influence before they are being sort of associated with the knot, and then after. And before, if we have just two points, then the before is not taken into consideration, and for the P1, and also it's not taken into consideration the part after for the point P2. All right. So the blending of these basis functions is happening between in the range between k and n plus 1. So we have more knots than just the control points. Actually, our B-spline will have n plus k knots, while the n is the number of control points and k is the degree of our, or k minus 1 is the degree of our polynomials. So k is really the number of knots which we need for defining one segment. Each B-spline has k plus 1 knots. So we have seen that our previous linear interpolation or linear segment has been defined between 1 up to 3. So we have 1 to 3 knots for the linear case. The B-spline curve overall is, as we said already, k minus 2 continuous. And as mentioned on the previous case, the basis function sum to 1. And for all parameter values between nodes k and n plus 1. Otherwise, their value is 0. That's why we have cancelled out the first part from the first b12 basis function and the second part from the b22 basis function. Let's have a look at the quadratic B-spline. Quadratic B-spline is defined with not 2 terms, but 3 terms. Here is 1 term, second term, and third term, and always for a particular range. So here we have between I, when u is between I and I plus 1, or here for I plus 1 and I plus 2, and here between I plus 2 and I plus 3. We are using in this formula here t, which is really in this case t is u minus I. So it was the same thing as we had before, but squared. And then we had this u minus I plus 1 will be then the t for the second part, which is the other quadratic segment. And the third quadratic segment will be the this part where the t is again defined through substituting the u, where u minus I plus 2 is defining the t. So we always sort of make out of the u something between 0 and 1, so that the parameter in the formula goes between 0 and 1. But in reality, the u goes between then, for example, I plus 2 and I plus 3, which would be, if I is 1, let's say, then it will be 3 and 4. And then for a quadratic formula, we will see that the formulation of our function looks like this. And we can see again the same thing happening. I will clear this out up a little bit so that we can see it more clearly, that again the first point is only weighted with the last part of the basis function, not with its first part. And the second point in the row is weighted with the middle part of the basis function, and the last point is weighted with the first one. And we will see right away why is this the case. If we have a look in here, we can see our how our basis functions are overlapping. These are the quadratic B-splines, and we can see that while here this part will be not contributing at all, because the sum of the basis functions in this region are not summing up to 1. And this is also the case here. The summing up to 1 starts actually from the point, from the node 3. And here we can see that our values for the first point, which we have, so this is our first point, the value will be weighted on the interval between 3 and 4, will be weighted with this part of the segment, the red part. And so this is the third part of our, so if we have this quadratic 3 segments, then we are using the third segment for our first point. So this is like the kind of a concave up uh, parabola, while this one would be the concave down part, and again here the concave up. So we can see here that the second point will be weighted with this segment with the orange um, uh, basis function. And obviously, the third point will be weighted with the third segment, the green one. Only this part will be between the values 3 and 4. So this will be a part between which, let's say, the function somehow at the beginning, the value of the first point has let's say, the relatively high contribution, the same as the second point. So it will start in the middle between the first and the second point. And then it will end up where it will end up here. It will end up where the first point had no contribution, and it will end up in the middle between the second and third point. We can see that they are meeting, their value is the contribution of the weights are equal here. So this is the first segment between the parameter interval between 3 and 4. And so on. And we can see that our uniform quadratic B-spline is actually not starting from the first point. We can hack it in such a way that it will be starting from the first point in case we will be adding some control points, some knots before. We will be multiplying the knots, but we will be talking about that in a moment. So already now you can see that some of the knots are sort of not contributing to the formation of the generation of the B-spline, and that depends on the degree of our B-spline. So it is an approximative curve, and it is approximative also in the way that it doesn't start from the beginning point, and it doesn't end in the end point. Also, we can see here the meaning of the term uniform. The uniform means that the knots are equidistant from each other, so there is uniformity in their placement, because they will also have the so-called non-uniform B-splines. And in those, we can place our knots arbitrarily on our interval. Even on the knots can be multiplied, meaning that there will be several knots associated with just one control point. We can also describe our splines, B-splines, through the basis matrix as we have done it before. So here, this will work in the same way that in our function, the first column will define the coefficients associated with the first polynomial associated with the first point, the second column with the second point, etc. We can see here a cubic B-spline. So this cubic B-spline will be formed by cubic polynomials for each of the segments, where this is the first segment, this is the second segment, this is the third segment, and this is the fourth segment. And for example, this fourth segment will be then used, for example, to be associated with the first point, while this segment will be then associated with the fourth point, which contributes to the blending of our B-spline curve. We can see that our B-spline curve can be of various degrees based on the K. So we have just one set of control points for all of these cases, and we are just varying the k parameter. And what we can see is that in the k case, this is the k equals 2, is the only case where we have an interpolating situation, where we have a piecewise linear polyline, while in the other cases, k equals 3, we will have a quadratic B-spline. In the k equals 4, we will have the cubic B-spline as the basis functions, and then we will have even higher degrees. And we can see that with an increasing amount of our degrees, our k, we are also having the curve more and more smooth, so more and more continuous, also across the knots. And it is also here visible that it's becoming shorter and shorter. So it starts to be formed later in stage than the lower degree polynomials. Finally, let's have a look, how do we calculate these basis functions, which we need for then performing our blending? Well, in the previous cases, as you remember, we have been always performing the computation of the constraints forming the constraint matrix, which were coming from the coefficients associated with the a's, and then we were inverting this constraint matrix so that we obtain the basis matrix. And this basis matrix was containing in the columns the coefficient associated with our basis polynomials. In the case of the B-splines, we will have a recursive calculation of the basis functions. So we have the one basis function, which is the initial one, is just something like a box filter. So it's equal to 1 for a certain interval ui to ui plus 1. So between two integer distance knots. And it is, if we have a look here, this is 1. So the k is 1, which means that the degree is of this B-spline is 0. So it's even not a linear, it's not even a linear interpolance. But we can generate the linear interpolance through this recursion. So let's have a look how we can do it. And then not only the linear ones, but also the quadratic, cubic, etc. So we have here the description of for the basis function, where the basis function IKU is equal to some term times, and here is the recursion going on, because here we have the k minus 1 u, and then plus something, some term, and here again the recursion is going on. So let's have a look at this formula, and let's calculate ourselves the coefficients for the linear interpolance. So if we have our case, which is the b and 1, 2 u, which is equal then to, and let's consider our uniform B-splines. So this will be u minus, and the knots will be at nice integer locations, u minus ui, the I is in this case 1, and we will have the ui will be 1. So, and divided by ui plus k, so 1 plus 2 is 3, minus 1 is 2, 2 minus ui u1. 2 minus 1 is 1. So maybe we can even delete it because we are otherwise having a fraction with the denominator 1. U minus 1 is the one term, and it is times the b1, comma, k minus 1, b11 u. And what is the b11 u? Well, it's 1, and it is, so we can again, we are multiplying this term by 1, which we can save ourselves the energy. So u minus 1, but we have the important information is on which range this function has these values. And that is, we have had 1, 1, so the I was 1, so this is between u1, I will just write the values, between 1, u, and 2. So this is one value, which we have computed. And plus this part. And this part is, now let's have a look, ui plus k. So this will be now 2 plus 1 is 3. 3 minus u. And now in the denominator is ui plus k, 3 minus ui plus 1 minus 2, 3 minus 2 is 1 again, so we do not write the denominator, times b I plus 1, so this will be b2 now, comma, k minus 1, b1 u. And the b1 u, the b2 1 is now again equal to, I will delete here these markings. B2 1 is again equal to 1 on a range, B2 between 2 and 3. And this will be 1, so I can delete it so that it's not that disturbing. And now, and I will just move this closer. Oops. So 2, 3, and this is our formulation for our basis function, which we are having for linear polynomials of our linear B-spline. The first one, we will also need to compute the B2 u, which will be in fact very similar. However, it will be then defined over a different range. So we can see here that the functions are can be recursively computed, and we have just now computed from the 0-degree B-spline coefficients, the first-degree B-spline coefficients. And from that, we can calculate the B-spline coefficients for the quadratic formula. Should we do it? No, I'm just joking. That would be a lot of work to do. So far, we have been covering only for the so-called uniform B-splines, which have their nodes equally distant from each other in the interval of our parameter. But then we can also have a definition of a non-uniform B-splines, meaning that the nodes are not equally distant from each other, and sometimes the nodes are even overlapping, so they are associated with the same point, control point. And this, the order of the nodes only has to be non-decreasing. So we can often have nodes which will have the same value, and that will lead to somehow a repeating knot, which can then with which we can then achieve something like the interpolation property, meaning that we can go through a point because we can force it by doubling the knot for that point. We can also add a point in the middle and not in the middle where we have already a fixed interval, and that will help us to keep, so it will then be a knot which will not have a integer value, but it will be a real valued knot, and this will keep us the locality property to be still preserved, so that with the, we will not have to recompute the entire curve. If we will be adding a knot at the end, then we will have to recompute the entire curve once again. So also, what is beneficial, if we are putting several knots at the beginning and at the end, we can achieve that the starting and ending points are then interpolated, which is usually not the case with the, which is not the case with the uniform B-spline, except of the linear case. In this case, the interpolation will look more nicer than at some node along the sequence, which is not the starting and ending point. The points along the sequence will usually be interpolated with some ugly shape, which is typically not so desired. So we can have an arbitrary amount of knots, in fact, in this non-uniform B-spline case, and therefore we can repeat a point in the through a having an associated knot, additional knot with that particular point. Okay. The non-uniform rational B-splines are another extension of the B-splines. So we have the non-uniform ones, meaning that our knots can be multiplied and can then form, for example, the interpolation of the starting or end points. And then we have an additional extension, which is called a rational B-spline. So from there, this abbreviation NURBS come from, which is sort of the state-of-the-art of flexibility of curves for computer-aided design. This formulation, which is here, so we can see that we have our points are associated with the basis functions, and also in the numerator and also in the denominator. Additionally, we have some scalar weight for each association with a point, and by the scalar weight, we can increase or decrease the influence of this point, and the multiplication of these two terms, which are then multiplied with the coefficients of our control point, are then used for in the denominator. And with this formulation, we can achieve that suddenly the B-splines can be used for a larger set of curves. Previously, we were using them for various flexible freeform curves, but the conical sections, like, for example, parabola or an ellipse, would not be possible to generate with the B-splines. However, this is possible with the rational component. So adding the rational component, we can expand the flexibility of the B-splines to support or to represent also the conical sections. And this is it today for Introduction to Curves in Computer Graphics. I thank you for your attention, and I'm looking forward to meet you at the next lecture.